So Wegener had this hypothesis in 1915 of continental drift, but despite all of his evidence of the continents fitting together like puzzle pieces and different rocks and fossils being similar across different continents, no one believed him, or at least it wasn't accepted in terms of the scientific academies because of these people called fixists. And these were people saying that continents were fixed in place. Many of them were geophysicists, and they posited that no forces that are known to humanity could cause the movement of the continents. And thus Wegener's proposal of continents plowing through the ocean floor simply didn't make any sense. But in the 1960s, through developments in technology, scientists were able to determine the features of the seafloor through bathymetric measurements. So bathymetry, remember, is the depth to the seafloor, and this is done through using technology called sonar. And sonar would send sound waves from a transmitter through the ocean down all the way to the seabed. Those waves would reflect off of the seabed and come back up and be captured and measured by a transducer on board a ship. And the travel time or length of time between the sending of the signal and the receiving of the signal allowed and still allows scientists to determine the distance of features from the sea to the sea floor. So this technology was actually developed for defense purposes by the United States government in order to locate and destroy German submarines during World War II, and also for mapping resources in the ocean like oil and gas. So after the 1960s, researchers considered that continents weren't plowing through the ocean floor, but rather being pushed around by it, and that ocean floor is constantly being created and destroyed or recycled. So we'll talk in the next few slides about the mobilist view. Harry Hess was one of the United States military men who later turned professor, who was the biggest advocate and most well known for this sonar technology and bathymetric measurements. And he was a proponent of seafloor spreading as a result of his measurements. So basically he would do cross sections of the ocean floors and find that the centers of them would be these raised areas 2 to 3 kilometers higher than the areas surrounding it. And the centers were known as, he coined the term as mid-ocean ridges, and then the areas surrounding it would be abyssal plains, and then once you reach continents, you would get to the continental shelf. And he proposed, based on his bathymetric measurements, that new ocean crust formed at these mid-ocean ridges, where young and hot magma material would rise up and then eventually explode out of the mid-ocean ridges and then cool and push out other material. And older ocean crust would be destroyed at deep sea trenches in other parts of the ocean. It's important to note that this movement of rock causes earthquakes and the observed bathymetric features. So that was the Hess hypothesis. It turned out to be true. Another larger-than-life figure in this revolution in scientific thought in the 1960s was a person named Marie Tharp, and she was the first person to create the World Ocean Floor Map. This one was published in 1977, and it shows the mid-ocean ridges in the center of oceans that effectively separate the continents, as well as many other features like seamounts, trenches, and abyssal plains. And it was with this work of mapping the entire seafloor that we were able to get a larger picture of the plate tectonic regime on Earth. Interestingly, the distribution of earthquakes on Earth matches pretty much exactly with the map of oceanic features and plate boundaries. And that was more evidence for a moving tectonic regime. So we note in this picture that earthquakes are not randomly distributed and they occur in certain locations. I'd ask you to if you can understand what the word random distribution means, if you could just draw a hypothetical random distribution of earthquakes on a map of Earth. Another line of evidence for the plate tectonic hypothesis came from the fact that igneous rocks record Earth's magnetic field in terms of its direction and its intensity. So when lavas cool, magnetic minerals statistically align with the direction and intensity of Earth's magnetic field. So as they go from liquid to solid, the magnetic minerals get frozen in time and in direction. Isotopic dating provides a time frame for these events of magnetization of the rocks. And they did this in the oceans, similar to sonar, this magnetometer technology developed in the 1960s, where they were able to tow a magnetometer behind a ship and measure the magnetic field coming off of the seafloor and of ships or sunken ships. Importantly, Earth's magnetic field, as represented by a dipole, can flip, so the north and south poles can reverse. And this has happened many times throughout Earth's history. What researchers did when they did transects of magnetic ocean floor measurements was that they found that different sections of ocean floor gave normal and reverse polarity magnetic directions. And from this, they developed something called a magnetic reversal chronology and were able to date other rock formations using these things called polarity crons. So on the left, you've got these polarity crons titled the Bruns, Matsuyama, Gauss, and Gilbert, and their age in terms of millions of years ago. So you can see that in all places on Earth, these crons do show up for the rocks of specific ages. Now, what this means in terms of mapping the ocean floor and determining plate tectonic theory was that these marine magnetic anomalies or changes in the direction of Earth's magnetic field were recorded on each side of the mid-ocean ridges. So we have these photo of the mid-ocean ridge in the center of each diagram, and as it spreads out further, we get different north pointing magnetic directions and south pointing magnetic directions for different periods of time. And the width of the strips is proportional to the length of time of the polarity crons. And in fact, I measured magnetic properties of rocks on continents for my PhD. So this work called paleomagnetism is still done a lot today. I measured some rocks in India and figured out the location of India in terms of latitude about 1 billion years in the past. If you're curious, I'd be happy to talk with you about it. So just to go over the summary of the development of plate tectonic theory, in 1915, Wegener proposed supercontinent Pangaea and continental drift. In 1960, Harry Hess proposed seafloor spreading, where the thinnest and youngest crust is in the center and it pushes out older and thicker crust. He also proposed subduction as a mechanism to destroy this crust that is always being created. In the 1960s, Marie Tharp mapped ocean floors to support seafloor spreading hypotheses. And then in 1963, the Vine-Matthews-Morley hypothesis came out for marine magnetic anomalies, showing that the ocean floor is in fact spreading over periods of Earth's history. We'll talk more about MMAs later. Actually, your lecture activity will be about MMAs. And by 1968, a model of plate tectonics with seafloor spreading and subduction was developed. So all of this happened within more or less a decade. This was a paradigm shift in Earth science, and it really helped us understand how Earth evolved. It wasn't that long ago, only about 60 years from today.